I'm Mounty. I'm a researcher here at the Silicon Valley AI Lab. And I'm going to talk about speech recognition. So hopefully Andrew's convinced you guys all of the importance of speech recognition as a problem for making progress in AI. So I'm going to dive right into how it works. I'll get into some of the technical details of that. In particular, I'm going to talk about how deep learning has been changing the landscape of speech recognition. So to start, I'll show you kind of what the current speech recognition pipeline looks like. Okay, so how does speech recognition work? Well, it starts with a snippet of audio, and someone has to have said something, and we take that snippet of audio and we feed it into what's called an acoustic model. And so we take that snippet of audio, chop it up into, say, 20 millisecond slices, feed that into the acoustic model. The job of the acoustic model is to predict what phoneme might be present in that audio. So a phoneme is just a unit of sound, and the acoustic model has to say what phoneme might be present. The acoustic model then feeds its predictions over phonemes into some kind of phoneme model. And this phoneme model, it can be as simple as a lexicon, a dictionary where you might look up words to phonemes. I'm hearing the reverb. Are you guys hearing that? Let's try without the microphone. Is that okay? Okay. So where was it? The phoneme model. Okay, so the phoneme model can be as simple as a lexicon where you might look up a word and its corresponding phonemes, or it could be some statistical model. And the phoneme model's job is to essentially say, given some predictions over phonemes, what words might be present. The phoneme model then feeds its predictions into the language model, and the language model's job is to assign to some string of words a probability. And if those words are likely to co-occur together, it will assign higher probability. If they're not likely to co-occur together, lower probability. So let's take an example of, say, the cat sat and the cat hat. So it's hard to distinguish between those two just based on the audio. The language model can then come in and say, well, the cat hat doesn't make any sense. That's not a sentence. So it can kind of come out and say the cat sat has to be the correct transcription. So this is just very much a cartoon of the speech recognition pipeline, today's kind of state-of-the-art speech recognition pipeline. But you can already see there are many components. And each one of these kind of modules has often several submodules. So it gets very difficult to reason about how to improve this system. So we want to make it a bit simpler. And to do that, we're going to use deep learning. Well, to start, we're going to replace the acoustic model with deep learning. And so actually, if you look under the hood of most state-of-the-art speech recognizers, what you'll find is something that looks very much like this, where you have a deep learning model for your acoustic model. That deep neural network's job is to essentially predict phonemes given small snippets of audio. Okay? And I'll explain to you guys how that works. So we take an audio waveform and we compute some kind of features from it. In this case, this is just a spectrogram. It's a windowed Fourier transform. Often the features are more complicated. We take the spectrogram and we chop it up into, say, 20 millisecond bins. And on top of each one of these bins, we plop a deep neural network. And like I said, the job of the deep neural network is to predict what phoneme might be present in that small snippet of audio. Okay? Now, in order to train this network, we need a data set, right? And if our input is 20 milliseconds of audio and our output is phoneme, we need a data set where every 20 millisecond snippet of audio is labeled with its corresponding phoneme. That's how supervised learning algorithms work. So where are we going to get such a data set? Well, most state-of-the-art speech systems are actually trained on something like 5,000 hours of speech. So it just doesn't make sense to have a human come in or several humans, and label on a 20 millisecond granularity what phoneme might be present. We're given a data set that's audio and the transcription. And from that, we need to produce 20 milliseconds where each 20 millisecond bin has its corresponding phoneme label. And it's intractable to have humans do that. So how are we going to do it? Well, say that we have the start of a sentence, the click brown, and its corresponding audio. Well, we take that transcription and we expand it into its phonemes. I just made these phonemes up, but they look something like that. We can take those phonemes and we can feed them along with the corresponding audio for this utterance. We can feed that both into what I'll call a bootstrapped speech recognizer, which is just essentially a speech recognizer that I've gotten from someone or I've kind of made through some mysterious process. But I'll take these phonemes and their corresponding audio, and I can actually use this speech recognizer that I have to align the phonemes to the data. So I might produce something like this using that recognizer, where I have each 20 millisecond slice of audio labeled with its corresponding phoneme. You see here the TH phoneme is assigned to the first three, the AH to the second two, so on and so forth. So this is how I build my training set with which I can then train my acoustic model. So I train my acoustic model, I retrain my speech recognizer, and then I take that newly trained recognizer and I repeat the process again. I align my data, and then I train another recognizer, and then I align the data again, and then I train another recognizer. And I just go around this cycle over and over again. And believe it or not, the alignment actually continues to improve. And so our speech recognizer continues to get better. So that's where the data comes from to train a current deep learning acoustic model. But as you can imagine, this process is somewhat brittle. Brittle in the sense that if you start out with something bad, you're going to end up with something bad. You can't bootstrap from something awful, right? And errors have a tendency to propagate. So again, we want to kind of remove this from our process. So I just showed you this picture. This is what the kind of current speech recognition pipeline looks like, where we have our deep learning model as an acoustic model. What we'd like to do is replace the entire thing with deep learning. And so deep speech, which is the system that we've been building here at Baidu, is a step in this direction. We haven't completely achieved this, but we've taken a big step in this direction. So I'll talk about how deep speech works now. There are three main ingredients for this system. The first is the model. This is the rocket ship, the rocket engine. And the model is based on a bidirectional recurrent neural network with a CTC, which stands for Connectionist Temporal Classification, which is a loss function which I'll describe in a little bit of detail in a moment. The second main ingredient is data. So that's the rocket fuel. So we need a lot of data. Where does that come from? Where do we capture such a huge amount of data? I'll talk a little bit about that. And the last most important thing is computation. When we have a lot of data and a huge rocket engine, we need a lot of computation to train this model efficiently. So I'm not going to talk about that very much because Brian has just kind of been over that. Suffice it to say that for our system, we use both a combination of model parallel and data parallel training on these 8 Titan boxes that make it efficient enough that, while it takes a little longer than 2 days, I don't complain to Brian too often. So why is the modeling in speech recognition hard? Well, speech recognition is challenging because the audio can have a variable number of time steps, right? The output can have a variable number of phonemes or words or letters. And of course, the two do not necessarily have to match, right? The audio does not have to have the same number of time steps as the corresponding transcription. So most of our traditional machine learning algorithms don't know how to handle this. So we need something special here. And what we need to be able to do is this algorithm we use, it needs to be able to do 2 things. So it needs to compute a loss function, given some audio input and a transcription output. It needs to be able to assign a score for the output given that audio input. That loss function, of course, needs to be differentiable so we can plug it into our gradient-based optimization algorithm and let the system learn. We also need to perform inference. So when we get some new input, some new data, some new audio that we haven't seen, we need to be able to find the transcription which is most probable given that audio under our current model. So I'm not going to talk about inference, but the way that we do it is essentially a beam search. It's a beam search, a modified beam search, which is not terribly complicated, so I'm not going to talk about that in the interest of time. So I'll talk a bit about the loss function and how that works, how we get around the alignment problem. So instead of using just a simple deep neural network, we actually use what's called a recurrent neural network. So probably a lot of you have heard of this recurrent neural network. And so briefly what that means is, say we have some audio input at time step t. The network at that time step is informed both by the audio input as well as the hidden state of the network at the previous time step. So it's able to process sequential data in that manner. Now the output of our system, instead of being phonemes, is actually just going to be letters. So this is what's called a grapheme-based system, where grapheme is the smallest unit of writing in a language. So it goes directly from audio input to a written transcription. In English, of course, this is just going to be the alphabet, and we throw in a space so we know that words have ended. Also crucial to the output is the blank character, which is essentially a null output. It lets the network say that I don't want to output anything at this time step. I want to contribute nothing to the current transcription. And the blank symbol is essential for us relieving ourselves of the alignment that I showed you earlier, the alignment process. So how do we get around that? Well, we use an algorithm called CTC, Connectionist Temporal Classification. And say that we have a transcription, the cat. One possible alignment would be the sequence of blanks, th, blank, 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 etc. And we just take that one possible alignment. We remove all the blanks. We collapse all the repeat characters that don't have blanks in between them. And so this, through those sequence of operations, becomes the cat. And rather than force the network to assign a score to one such alignment, we let it assign the score to all possible alignments of blanks and letters which map to the cat under the operations I just explained. So one way you could imagine doing this is simply by delineating all such possible alignments, computing the score of the network for each one of those alignments, and then summing them up. Of course, you're probably thinking that there are a lot of such alignments, and it would not be tractable to do that. So CTC, which is this algorithm I've been telling you about, actually gives us a very simple dynamic programming method of doing this efficiently. And it's actually basically a vanilla dynamic programming algorithm, which has a couple of modifications to account for the blanks and the repeats. So I won't go into the dynamic programming algorithm, but intuitively, what it's doing is delineating all possible alignments and letting us sum up over the score of all of those so that we integrate out the alignment and just give a score to the transcription cat. So that's how the model works. Now, where does the data come from? Well, we have many thousands of hours of real data, but we need a lot of rocket fuel for this system. So we turn to computer vision as inspiration in our case. And one thing that's commonly done in computer vision is to take an image and shift it around in such, change it in ways such that the label is preserved. So you can do very simple things to this picture. You can translate it, shift it left and right. You can reflect it about its vertical axis. You can rotate it. In all of these cases, a human would still recognize this as a house. But in all of these cases, the pixels look very different to the machine. So it's actually allowing it to learn a little bit more about this image, what a house is. So how can we do this in audio? Well, it's not as simple in audio to know what kind of transformations you can make to an audio signal which also preserve the meaning, the speech. It's very easy to take an audio signal and speed it up, and all of a sudden it doesn't sound realistic, and we shouldn't, we don't want to train our network on non-realistic speech. While perhaps that might, it's the data that we care about our speech recognizing will not sound like that, so it's wasted effort. So one thing we can do, very simple, is take some clip. So in this case, this is me.
The quick brown fox jumped over the lazy dog.
So that was me saying the quick brown fox jumped over the lazy dog. And we can take to that clip, we can add some noise. And we end up with
The quick brown fox jumped over the lazy dog.
So for those of you in the back that couldn't hear that, that was essentially a clean snippet of audio, a clip of noise. We've literally added them element-wise and produced what sounded very much like a noisy, like me saying the quick brown fox in some noisy background. And then we can take, a whole bunch of different noise clips and add them all to this speech signal and train our network on those. So we started with about 2,000 hours of publicly available data. These are all public data sets. We added about 5,000 hours of our own speech data we collected ourselves. This is all raw data. This is real transcribed speech. But that wasn't enough. So to that 7,000 hours, we repeated it over and over again with different snippets of noise and created over 100,000 hours of synthesized audio. And with all this data, we trained our network. And it could even use more than that. So this has all been in English that I've been talking about. And we kind of released some results about our English system in December. And it does quite well. On a test set we collected, it did better than a lot of our competitors. But I actually want to talk a little bit right now about how we've successfully ported our system to Mandarin. So this is work that actually Ryan Prenger, who's here, Tony, who was here earlier, I don't know if he's still here, they led a lot of this work early on. And Ryan's going to show you a demo in a few minutes of our system. But I'll talk to you briefly about how we were able to port it to Mandarin. So what's hard about Mandarin? Well, a couple things. First of all, Mandarin is a tonal language. So what does that mean? Well, you have here essentially 5 different words that to me all sound like ma. But to a Chinese speaker, they have very subtle changes in pitch, which changes the meaning of the word. Now in English is pitch invariant. So if I say word or word at different pitches, it means the same thing. So it's actually a desirable property of a speech system to have it be pitch invariant. And all the years of research that were done on English speech recognition actually made those systems somewhat pitch invariant. So this has been a challenge for Mandarin speech recognition, at least with traditional systems. With our system, however, since we did very little processing of the audio, we expected or we hypothesized that the network would be able to learn tonal information on its own, just by being given very minimally pre-processed audio and the corresponding correct label. So we actually did not do much in the way of changing our system to be to account for the fact that Mandarin is tonal. But we speculated that it might be a problem. Another potential issue is, in English we have 26 letters in the alphabet. In Mandarin there are, speculated to be about 80,000. I haven't, nobody actually knows how many there are, but there are something like 80,000 characters in a complete dictionary. And so the output of the system, if we wanted to include all 80,000 characters, would be huge. This isn't just a problem in terms of computation, where the output layer of the network gets very expensive. It's also a problem because it's unlikely that in our speech data we will even have all of these characters represented, because we would need an exorbitant amount of speech data for that. So one thing we thought about was using Pinyin. So for those of you that don't know, Pinyin is a phonetic transcription of Chinese. It's basically the alphabet with tonal marking, something like that. And for us, using Pinyin was kind of a step in the wrong direction. I was moving back towards a phoneme-based system. The other problem with Pinyin is that even going from Pinyin to characters is tricky and not 100% guaranteed to be accurate. So we really didn't want to use Pinyin. So, well, luckily for us, it turned out that if you look at the character set of what people say, 99.9% of what people might say is encapsulated by about 5,000 or 6,000 characters. So rather than using the full 80,000 characters, we used about 5,000 or 6,000 of which consists of the things that people might say. And that basically covered all possible things for us. And so this was computationally difficult, but thanks to the hard work of our HPC experts, we were able to actually train these systems quite efficiently. So where did this leave us? Well, we started working on this in February. Ryan and Tony started working on this in February. And our first system was about 16% character error rate, where character error rate is the edit distance between two character strings divided by the length of the ground truth. And after only a few short months, thanks to iterating through our research cycle extremely quickly, our system is now at about 6% character error rate. And to the best of my knowledge, we actually have the best Mandarin voice query speech recognizer in the world. And so it's really good. I mean, unfortunately, I can't test it myself because I don't speak any Chinese. But I've been told that it's very, very good. So I'm actually going to let Ryan demo it for you. And for those of you that don't speak Chinese, hopefully someone trustworthy will verify that it's correct. So do you want to come up and...
If you're wondering why I'm going to do the demo, because of all the people who are willing to speak Mandarin in front of you, I'm the worst. So this is like, if it gets any of the characters right, it's a super awesome system. How many people speak Chinese? Okay, so you can check.
Do you want to wear the mic?
It's okay. I mean, I can't, but it's up to you. Okay,
I'll just stand close to you.
Okay, so I'll start off something I can say. 我会说一点普通话.
So what does that mean?
Is that right? So here's one I want to try because this sometimes works and it's very cool when it does. Okay. 我想要 iPhone.
The laughing at the end might be hard.
Oh, iPhone. Okay. So we're like doing an all character-based language model, right? And we realized, oh, wait, there's English characters in our training set. Well, we'll just leave them in there. And the network just figured out how to switch between languages. So that's actually pretty cool because we didn't build that in or anything. So it often spells phone. I think the clapping at the end made it sound more like phono. I don't know. Yeah. So when it was transcribed, some words now are like English words and they were transcribed actually with English characters. So you could try to phonetically spell it out with Mandarin, but I think we move into a more globalized world. We're going to have this switching thing, and it's nice if you can have a system that can just absorb it and not have to build it in. Yeah, so let me try one more that I learned a few hours ago. 我们在招聘. I probably cut off the P at the end. All right. So that's supposed to be we are hiring. So just so you know. Oh, would an actual Mandarin person like to try speaker to show that
Yeah, come on.
it's not rigged because this is how we would rig. So what I supposed to do? Sorry. So I'll just press a button, then you speak, then I'll press it again. 我们在百度.
Thank you. Okay, so that was actually all I have. Do you guys have any questions?